Look up at the night sky, really look at it. Those pinpricks of light, the stars we've mapped and named, seem to promise familiarity, as if the universe is a place we know. But between them, there's a hidden frontier, a silent ocean of darkness so vast it defies comprehension. This isn't just empty space. It's a realm where the rules of physics twist into riddles, where particles we can't see shape galaxies, and where planets drift alone, untethered from any sun. Think of it, for every star you can spot with the naked eye, there are countless mysteries lurking in the shadows, waiting to rewrite what we thought we knew about the cosmos. What if I told you that the blackness between stars isn't black at all, that it's alive with invisible forces, strange matter, and objects so elusive they slip through our finest telescopes like ghosts? Scientists call it the interstellar medium, a poetic name for a place that's anything but gentle. Here, temperatures swing from near absolute zero to millions of degrees. Gas clouds dense enough to birth stars float beside voids so empty they could swallow our solar system without a trace. And then there's the real enigma, dark matter, an unseen hand guiding the dance of galaxies, making up most of the universe's mass yet leaving no trace we've been able to catch. It's as if the cosmos is playing a game of hide and seek, and we're only just beginning to learn the rules. This journey isn't just about filling in gaps on a star map. It's about confronting the humbling truth that what we see is only a fraction of what's out there. Every discovery in these uncharted reaches forces us to rethink our place in the universe. Could rogue planets flung from their home systems carry the building blocks of life? Might dark energy pushing the cosmos apart one day tear everything we know to pieces? The answers, or the search for them, could redefine existence itself. So let's dive into the deep beyond the light, into the spaces where science blurs into wonder. By the end, you won't just see the night sky differently. You'll feel it calling to you, whispering of secrets we've yet to uncover. Even the emptiest corners of space hold more than meets the eye. Picture a single atom floating in a box the size of a sugar cube. That's the ghostly density of interstellar space. But this near-nothingness crackles with hidden activity. Charged particles, remnants of ancient supernova, zip through magnetic fields like cosmic pinballs. Delicate filaments of dust, finer than smoke, drift for light years before coalescing into the seeds of new solar systems. It's a place where chemistry happens in slow motion, where molecules like hydrogen and helium bond over millennia in the cold dark, forming fragile clouds that glow faintly when starlight brushes them. These vast interstellar clouds are cosmic nurseries. Gravity tugs at their wisps, compressing them over eons until pockets ignite into newborn stars. But between these glowing cradles lie regions so empty they challenge our understanding of physics. In the Boötes void, for instance, a space spanning 300 million light-years contains barely 60 galaxies. To put that in perspective, our local neighborhood would fit inside it thousands of times over. Yet even here, quantum fluctuations whisper virtual particles blinking in and out of existence, proof that true emptiness might not exist at all. What's truly startling is how these sparse ingredients shape the universe. That wispy interstellar gas, it carries traces of elements forged in dying stars: carbon, oxygen, iron, the same atoms that now make up our bodies. The dust grains, no larger than a virus, act as cosmic refrigerators, radiating heat away until clouds collapse into stars. And threading through it all are magnetic fields, invisible rivers of force that guide cosmic rays and sculpt the birth of galaxies. We're only beginning to decode this delicate ecosystem, one where even the void hums with unseen energy. Every probe we send, every radio telescope listening to the whispers between stars brings us closer to answering the fundamental question: how does nothingness create everything? Dark matter is the universe's best-kept secret, a ghostly presence that outweighs everything we can see by a factor of 5, yet refuses to show itself. Picture a spiderweb stretched across the cosmos, its threads invisible but strong enough to bend the paths of entire galaxies. That's dark matter's grip. Without it, stars on the outer edges of spiral galaxies would fling into the void, moving too fast for gravity alone to hold them. But something unseen anchors them, a hidden hand we've only detected by the way it warps space itself. Take the Bullet Cluster, one of the most striking clues we've found. When two galaxy clusters collided, their visible gas clouds smashed together and slowed down, but their dark matter kept right on going, slipping through the crash like a phantom. X-ray telescopes saw the aftermath, a separation between the glowing hot gas and the mass-distorting spacetime. It was as if the universe had drawn us a map, highlighting where the real weight of the cosmos actually lies. The hunt for dark matter's true nature is a puzzle with pieces scattered across disciplines. Some scientists think it's made of WIMP, weakly interacting massive particles that barely touch ordinary matter, drifting through your body by the billions every second without a trace. Others propose actions, particles so light and elusive they behave more like waves than matter. Then there are the boldest ideas, that dark matter isn't particles at all, but primordial black holes left over from the Big Bang, or even evidence of an entirely new dimension brushing against our own. What's clear is that dark matter doesn't just lurk in the voids between stars, it sculpts them. Simulations show how its gravitational pull gathers ordinary matter into the filaments of the cosmic web, guiding the birth of galaxies like an invisible architect. Without it, the universe would look radically different: fewer galaxies, no grand structures, just a diffuse haze of gas. Yet for all its influence, dark matter remains maddeningly aloof. The world's most sensitive detectors, buried deep underground to shield from cosmic noise, still wait for that elusive signal, that faint bump in the night, proving we're not alone in the universe, just surrounded by something we can't see. The irony is haunting. We're made of the rarest stuff in existence, the ordinary matter that accounts for barely 5% of the cosmos. The rest is a mystery written in gravity's handwriting, a reminder that what we call reality might just be the tip of an iceberg floating in an unseen sea. Every galaxy, every star, every atom in your body moves to the rhythm of forces we're only beginning to sense. And somewhere in the dark between the stars, the answers wait. Rogue planets are the universe's silent drifters, worlds without suns, wandering the cosmic dark like lost travelers. Imagine Earth ripped from its orbit, flung into the abyss until the sun shrinks to just another star in the distance. That's the reality for these nomadic worlds, and there might be more of them in our galaxy than stars themselves. Some were born alone in the collapse of gas clouds too small to ignite a star. Others were violently ejected from their home systems by gravitational chaos, sent careening into the void where no sunlight ever warms their surfaces. Detecting these lone wanderers is like searching for a black marble in a pitch-black room. Without starlight to reflect, they're nearly invisible, but not entirely. Occasionally, their gravity bends the light of distant stars behind them, a phenomenon called microlensing that briefly magnifies the star's glow like a cosmic magnifying glass. Through these rare flickers, astronomers have estimated there could be 20 rogue planets for every star in the Milky Way. That's hundreds of billions of worlds adrift in the darkness, each a potential time capsule from the early solar system. What's astonishing is that some of these planets might not be frozen wastelands. Tidal forces from their moons or radioactive decay in their cores could keep subsurface oceans liquid for billions of years. Picture a planet like Jupiter's moon Europa, but untethered from any star, a dark, icy shell hiding warm, salty waters where life could cling. If microbes thrive near hydrothermal vents in Earth's deepest oceans, why not in the hidden seas of a rogue world? Some scientists even speculate that these planets could act as interstellar arcs, carrying life between stars over cosmic timescales. The implications are staggering. If life can persist in the eternal night between stars, it would mean the universe is far more resilient and far stranger than we ever imagined. Rogue planets challenge our definition of habitable. They force us to ask, does life need a sun or just energy and chemistry? Every microlensing event, every faint infrared signature we capture brings us closer to answering that question. These cosmic orphans might hold clues to how planets form, how solar systems evolve, and whether life is a rare fluke or a common thread woven through the fabric of the cosmos. And then there's the chilling possibility that one could be closer than we think. A rogue planet drifting through our outer solar system would be nearly impossible to spot unless it passed directly in front of a star. Some theorists suggest that gravitational anomalies in the Kuiper belt could hint at an unseen, Earth-sized wanderer passing through, a ghost in our own celestial backyard. Whether they're ancient relics or hidden oases, rogue planets remind us that the universe is full of surprises, and the greatest discoveries might be lurking in the places we least expect. Those specks of interstellar dust so small you could fit 1,000,000 of them on the head of a pin are cosmic alchemists. Floating in the void, they might seem insignificant, but they're anything but. Each grain is a tiny laboratory where chemistry plays out on an atomic scale. Picture this, a microscopic fleck of silicate or carbon, barely wider than a strand of DNA, drifting through the frigid expanse between stars. Starlight nudges it, cosmic rays bombard it, and on its surface, molecules cling like frost on a windowpane. Over eons, these grains become cradles for water ice, carbon monoxide, and even complex organic compounds like formaldehyde or methanol. What's astonishing is how much these minuscule particles shape the universe. They're the reason the Milky Way's core appears veiled in crimson. Dust scatters blue light, leaving only the red to reach our telescopes. They're the reason newborn stars flicker into view like lights turning on behind a curtain. But their true magic lies in their chemistry. In the cold, near-perfect vacuum of space, atoms move sluggishly, yet on dust grains they find a foothold. Hydrogen meets oxygen, forming water. Carbon chains grow into the building blocks of amino acids. Some of these grains, forged in the death throes of ancient stars, carry presolar material older than our solar system itself. The implications are staggering. When a new planetary system forms, these dust grains, now packed into comets and asteroids, deliver their chemical bounty. Earth's oceans, the carbon in your cells, even the molecules that sparked life might trace back to these interstellar travelers. The Murchison meteorite, a space rock that fell in Australia in 1969, contained over 90 amino acids, many never seen on Earth. It's proof that the universe is prepping the ingredients for life long before planets even exist, and the mystery deepens. Recent telescope observations reveal that some dust grains are fluffier than expected, more like snowflakes than solid specks. Others spin at dizzying speeds, propelled by starlight like cosmic windmills. Then there's the enigma of polycyclic aromatic hydrocarbons, tough, carbon-rich molecules that glow in infrared and might be the most abundant organic compounds in space. Could they have been the scaffolding for early life? The next time you look up at the night sky, remember, the darkness isn't empty. It's a factory, a conveyor belt of chemistry on a galactic scale. Those tiny dust grains, invisible to the naked eye, are weaving the story of everything from the birth of stars to the origins of life itself, and we're just beginning to read the tale. Every second, invisible bullets tear through the cosmos subatomic shrapnel, moving so fast they could circle Earth 7 times in the blink of an eye. These are cosmic rays, fragments of atoms stripped down to their cores and hurled across the galaxy with unimaginable force. Most are protons, the building blocks of atomic nuclei, but some carry the fingerprints of heavier elements like iron or even carbon. They've traveled millions of years, threading through magnetic fields and gas clouds, only to end their journey by colliding with our atmosphere in a silent burst of secondary particles. Where do these high-speed travelers come from? The strongest clues point to cosmic cataclysms. Supernova. The explosive deaths of massive stars likely act as natural particle accelerators, their shockwaves whipping charged particles to near light speeds. But some cosmic rays pack so much energy that even supernova can't explain them. These ultra-high-energy particles might originate from active galactic nuclei, where supermassive black holes spew jets of plasma across millions of light years. Or perhaps they're born in the chaotic mergers of neutron stars, events so violent they ripple space-time itself. The real puzzle isn't just their origin, it's their path. Cosmic rays don't travel in straight lines. The galaxy's tangled magnetic fields bend their trajectories, turning them into cosmic pinballs. By the time they reach us, their directions are scrambled, erasing any trace of their birthplace. It's like trying to find the source of a river when you're standing in the ocean. Scientists have to work backward, studying the particles' composition and energy to piece together their history. What they've found is startling. Some cosmic rays carry isotopes of elements like beryllium or aluminum that decay over time, acting as atomic clocks. By measuring these isotopes, researchers can estimate how long the particles have been journeying through space, often tens of millions of years. Others reveal traces of antimatter, hinting at environments where matter and antimatter collide in fleeting bursts of energy. Then there's the mystery of the knee and the ankle. When scientists plot cosmic ray energies on a graph, there's a sudden bend, a knee, around 1 quadrillion electron volts, where the number of particles drops sharply. This suggests different acceleration mechanisms at work. Beyond that, at energies 100 times higher, the ankle appears, marking another shift. Whatever's creating these ultra-high-energy rays operates on a scale we've yet to comprehend. But here's the twist: cosmic rays aren't just messengers, they're makers. When they slam into interstellar gas, they trigger nuclear reactions, forging rare isotopes that wouldn't form otherwise. Some researchers believe these collisions could even produce lithium, beryllium, and boron, elements that are scarce in the universe but crucial for life. In a way, every atom in your body might owe its existence to cosmic rays that struck gas clouds billions of years ago. The next time you feel a breeze, remember, you're also being gently bathed by particles from the far reaches of the galaxy. They've crossed deserts of darkness, dodged black holes, and survived magnetic maelstroms, all to whisper secrets about the universe's most violent corners. And we're just learning how to listen. One moment there's silence, the next, a blip of radio energy so intense it outshines entire galaxies for a fraction of a second. Fast radio bursts, or FRB, are the universe's most enigmatic Morse code, flickering across the cosmos with no obvious explanation. First detected in 2007, these bursts pack more energy than the sun emits in 80 years, yet they vanish before you can blink. Some erupt once and never repeat, like cosmic firecrackers. Others pulse on a schedule, ticking away with eerie precision, and their origins still anyone's guess. Take FRB 1211, the first repeater ever found. Nestled in a dwarf galaxy 3 billion light-years away, it flares up unpredictably, sometimes hurling dozens of bursts in a single hour. Then there's FRB 1820, which spins like a lighthouse, emitting bursts every 16 days as if something or someone is winding a cosmic clock. The strangest part, these signals are stretched, their lower frequencies arriving slightly later than the higher ones. It's as if they've battled through clouds of ionized gas, a fingerprint of the intergalactic medium they've traversed. So what's behind these celestial fireworks? The theories are as wild as the bursts themselves. Magnetas neutron stars with magnetic fields so strong they could strip atoms apart are prime suspects. Picture a starquake on one of these hyper-dense objects, its crust cracking like an eggshell, releasing a tsunami of radio waves. Or imagine a pulsar's beam sweeping past Earth, its lighthouse-like signal amplified by intervening plasma. But some FRBs defy even these exotic explanations. Their energies are too extreme, their patterns too precise. Could they be the aftermath of colliding neutron stars or black holes swallowing dense stellar corpses? Then, of course, there's the elephant in the room, alien technology. While most scientists lean toward natural causes, the sheer power and structure of some bursts raise eyebrows. A civilization advanced enough to harness a star's energy might use focused beams for propulsion or communication, and an errant pulse could sweep across our telescopes like a stray headlight in the cosmic fog. The truth, we're still listening. Projects like the Canadian Hydrogen Intensity Mapping Experiment, or CHIME, scan the sky daily, cataloging new bursts while hunting for clues in their echoes. What's clear is that FRBs are more than cosmic static. They are probes. Each burst carries a snapshot of the material it's passed through, mapping the otherwise invisible web of gas and magnetic fields between galaxies. Some might even help solve one of astronomy's biggest headaches, the missing matter problem. The universe's visible mass doesn't add up to predictions, but FRBs could reveal where the rest is hiding, trapped in diffuse ionized gas too faint to see. Every time a new burst crackles into our detectors, it's a reminder of how much we don't know. The voids between stars, once thought empty, are crackling with activity, some natural, some perhaps beyond our current understanding. Whether they're the death cries of collapsed stars or something far stranger, one thing's certain: the cosmos is sending us messages. We're just learning how to decode them. At the smallest scales imaginable, the universe doesn't behave like a calm, smooth pond. It churns. Picture space-time not as a blank canvas but as a bubbling cauldron, where particles flicker into existence and vanish again in less than a trillionth of a second. This is quantum foam, the turbulent foundation of reality itself, where the very fabric of space and time becomes jagged and uncertain. According to quantum mechanics, empty space is anything but empty. It's a seething maelstrom of virtual particles, popping in and out of existence thanks to the strange rules that govern the subatomic world. These fleeting disturbances are so tiny they'd make an atom look like a galaxy by comparison, yet their effects might ripple across the cosmos in ways we're only beginning to grasp. One of the most mind-bending implications of quantum foam is how it could warp the path of light traveling across the universe. Imagine a photon, a particle of light, journeying for billions of years from a distant quasar. As it traverses the frothy texture of space-time, it doesn't glide smoothly, it stumbles ever so slightly over the microscopic bumps and dips of this quantum landscape. Over vast distances, these tiny detours could add up, subtly distorting the light's arrival time or even its energy. Some scientists speculate that this effect might explain why ultra-high-energy cosmic rays don't behave quite as expected. Their paths could be nudged by the foam's invisible turbulence. Then there's the eerie possibility that quantum foam might hold clues to the unification of physics' greatest theories, general relativity and quantum mechanics. Einstein's relativity paints space-time as a smooth, flexible sheet, bending under the weight of stars and galaxies. Quantum mechanics, on the other hand, describes a chaotic, probabilistic world where certainty dissolves. Quantum foam sits at the crossroads, a place where both theories collide literally. At scales a billion trillion times smaller than an atom, space-time itself may dissolve into a probabilistic froth, where concepts like here and now lose all meaning. The challenge: we can't observe it directly. The energy required to probe such tiny scales is beyond anything our particle accelerators can muster. Yet indirect hints keep tantalizing us. Some models suggest that if quantum foam exists, it could leave faint fingerprints on the light from gamma-ray bursts, those colossal stellar explosions that flare across the universe. By studying how different wavelengths of light arrive at our telescopes, some slowed ever so slightly by the foam's texture, we might finally glimpse this hidden layer of reality. Other theories propose even wilder ideas, that quantum foam could harbor miniature wormholes, fleeting tunnels through space-time that blink into existence and vanish before anything can pass through. But here's the real twist: quantum foam might not just be a curiosity of the ultra-small. Its effects could scale up, influencing the vast voids between galaxies. If space-time is inherently frothy, then the nothingness we perceive in cosmic voids might actually simmer with latent energy, a kind of quantum static humming beneath the surface of reality. This could reshape our understanding of dark energy, the mysterious force accelerating the universe's expansion. Perhaps dark energy isn't some exotic substance, but the cumulative effect of countless quantum fluctuations, a sea of microscopic ripples pushing the cosmos apart. The deeper we dig into quantum foam, the more it feels like peering into a funhouse mirror, one that distorts not just space, but our very notions of what's real. It's a reminder that the universe is far stranger than it appears, and the emptiest corners of space might be the most alive with secrets. Every time we think we've grasped the rules, the cosmos whispers back, "Look closer." There's always another layer, another mystery woven into the fabric of the void. The Oort Cloud is the solar system's final boundary, a vast, silent reservoir of ice and rock stretching so far into the void that the sun's gravity barely holds it in sway. Imagine a sphere of frozen relics, some as large as mountains, drifting sluggishly in the deep freeze of space, nearly a light year from Earth. This isn't just a distant curiosity. It's a time capsule from the dawn of our solar system, preserving the raw materials that never coalesced into planets. And here's the twist: we've never seen it directly. Its existence is inferred from the long-period comets that occasionally streak into the inner solar system, their elongated orbits pointing back to this icy halo like cosmic breadcrumbs. What makes the Oort Cloud so fascinating is its sheer scale. If you shrunk the solar system to the size of a football field, the planets would crowd within the inner few yards. The Kuiper belt home to Pluto would sit near the edge of the end zone, but the Oort Cloud, it would begin miles beyond the stadium, stretching into the next town. Some estimates suggest it contains trillions of objects, a frozen swarm so sparse that a traveler passing through might not even notice them. Yet collectively, they represent a staggering mass, possibly several times that of Earth. Then there's the mystery of its formation. The Oort Cloud's icy denizens weren't born this far out. They were likely flung here by the gravitational tug of war between the young gas giants, a cosmic game of pinball that scattered debris to the solar system's outermost fringes. Over billions of years, passing stars and galactic tides molded this chaos into a loose shell, a gravitational net catching the remnants of our solar system's infancy. But the Oort Cloud isn't just a relic, it's a gateway. In 2017, the interstellar object Oumuamua tore through our solar system, its speed and trajectory suggesting it came from another star. Then, in 2019, Comet Borisov followed, trailing gases unlike anything in our cosmic neighborhood. These visitors hint that the Oort Cloud might be a crossroads, where objects from other stars occasionally pass through or even get captured. Could some of its icy bodies be interstellar hitchhikers, snatched by the sun's gravity eons ago? If so, studying them would be like cracking open a cosmic message in a bottle, revealing the chemistry of distant star systems. The most tantalizing question, though, is what else might lurk out there. The Oort Cloud's distance makes it a perfect hideout for objects we've never detected. Perhaps even a stealthy, Earth-sized world ejected early in the solar system's history. Some theorists speculate that a hidden Planet 9 could be shepherding the orbits of distant objects, its gravity sculpting their paths from the shadows. Others wonder if the cloud might harbor rogue planets from other stars, frozen nomads drifting between solar systems. One thing's certain, the Oort Cloud is more than a graveyard of ice. It's a dynamic frontier, a place where the solar system blurs into the interstellar deep. Every comet that visits us from its depths carries a fragment of that story, a whisper from the cold, dark edges of our cosmic home. And as our telescopes grow sharper, we might finally begin to read those whispers, unlocking secrets not just about our past, but about the untamed wilderness between the stars. Stretching between stars like unseen highways, interstellar magnetic fields are the silent architects of our galaxy. Though invisible to our eyes, their influence is everywhere, guiding the flow of gas, sculpting vast dust clouds, and even bending the paths of high-energy cosmic rays. Picture the Milky Way not just as a collection of stars, but as a labyrinth of magnetic threads, some stretching tens of thousands of light years, their delicate pull shaping the universe on scales we're only beginning to measure. These fields are born from chaos. When a massive star explodes as a supernova, its death throes send shockwaves rippling through space, churning charged particles into turbulent currents. Over time, these currents organize into vast, coherent structures like cosmic rivers of force. In places, the fields align into ordered filaments, weaving through nebulas so precisely they resemble the grain in a piece of celestial wood. Elsewhere, they twist into knots, storing energy like loaded springs until they snap, releasing bursts that accelerate particles to nearly the speed of light. One of their most astonishing roles is in star formation. Without magnetic fields, collapsing gas clouds would simply shrink into stars unimpeded. Instead, the fields act as cosmic brakes, resisting gravity's pull and slowing the process over millions of years. They channel material into spinning disks, creating the nurseries where planets eventually coalesce. In the Orion Nebula, for instance, astronomers have mapped fields so strong they align newborn stars like pearls on a string, their magnetic fingerprints visible in the polarized light glowing from surrounding dust. But mapping these fields is like tracing the outline of a shadow. Scientists rely on subtle clues, the way dust grains align like compass needles in the galactic wind, or how certain molecules emit polarized radio waves, their signals twisted by the magnetic environment. Recent advances with telescopes like the Stratospheric Observatory for Infrared Astronomy, or SOFIA, have revealed fields threading through even the emptiest voids, their presence betrayed by faint infrared glows from aligned dust particles. Perhaps the most startling discovery is how these fields connect seemingly isolated regions of space. A flare from a distant quasar can ripple along magnetic lines, transferring energy across light years like a cosmic game of telephone. Some researchers speculate that galactic-scale fields might even funnel material between galaxies, weaving the universe into a single, interconnected web. Yet for all their power, these fields are fragile. The energy stored in the Milky Way's magnetic web is a mere whisper compared to gravity's roar, about 1/1,000,000th the strength of Earth's own magnetic field at its surface. But over cosmic distances, that whisper becomes a shaping hand, quietly orchestrating the dance of matter across the void. Every time a star is born, a cosmic ray deflected, or a nebula sculpted into delicate tendrils, it's a reminder. The emptiest spaces are alive with invisible forces, and the universe hums with currents we're just learning to trace. Imagine a bubble so vast it could swallow thousands of galaxies whole, yet inside, there's almost nothing. This is the eerie reality of cosmic voids, regions of space so empty they make the black between stars seem crowded. The Boötes void, one of the largest ever discovered, spans 330 million light-years but contains fewer than 60 galaxies. If our Milky Way sat at its center, we wouldn't have known other galaxies existed until the 1960s. These aren't just gaps in the cosmic web, they're staggering absences that rewrite our understanding of how the universe structures itself. What's baffling is how these voids form. According to leading theories, they're not so much holes as they are the negative spaces in a sponge, shaped by the universe's earliest moments. In the infant cosmos, quantum fluctuations created tiny density variations, some regions slightly denser, others slightly emptier. Over billions of years, gravity amplified these differences, pulling matter into filaments and leaving behind these cavernous voids, but the scale is all wrong. Simulations predict voids about 1/10 the size of what we observe. Some process we don't yet understand must be accelerating their growth, like an invisible hand stretching the fabric of nothingness itself. Then there's the mystery of what or isn't inside. These voids aren't perfectly empty. Floating in the darkness are void galaxies, lonely outposts that somehow survived the evacuation. They're unlike any others in the cosmos, smaller, bluer, and strangely isolated, as if stranded on cosmic islands. Without neighbors to collide with, they've missed the usual galactic growth spurts, preserving clues about how galaxies evolve in extreme isolation. Even here, the void isn't entirely dead. Recent observations reveal faint tendrils of hydrogen gas threading through the emptiness, leftovers from the universe's primordial soup. But the real enigma is dark energy's role. As the universe expands, voids grow faster than denser regions, their emptiness offering less gravitational resistance. Some theorists suggest these voids are dark energy's fingerprints, places where its repulsive force operates unchecked. If true, studying them could reveal why the universe's expansion is accelerating and whether dark energy's strength changes over time. The most unsettling possibility, voids might be hiding something. Quantum physics suggests that even perfect vacuum seethes with energy. Could these vast expanses harbor exotic particles or fields we've yet to detect? Or more chillingly, might they be evidence of a collision with another universe, a cosmic bruise left by a long-ago encounter with a reality beyond our own? For now, voids remain the universe's quietest rebels, regions where the rules seem different and our theories falter. They remind us that what we call nothing is never truly empty, just waiting to be understood. Neutrinos are the universe's ultimate ghosts, particles so elusive they slip through planets like they're not even there. Picture this. Right now, as you watch this, trillions of them are passing through your body, straight through the floor beneath you, and out the other side of Earth without a single collision. Born in the nuclear furnaces of stars, the cataclysmic explosions of supernova, and even the violent jets of black holes, these phantoms carry secrets from the most extreme environments in the cosmos. Yet they barely leave a trace, making them both a detective's dream and nightmare. Take the Sun, for example. Every second, it floods space with 65 billion neutrinos per square centimeter. These particles are born deep in the solar core, where hydrogen fuses into helium under crushing pressure. Unlike photons, which take thousands of years to zigzag their way to the surface, neutrinos zip straight out at nearly the speed of light. They're the only direct messengers from the Sun's heart, offering a real-time snapshot of its nuclear reactions. But catching them is like trying to trap smoke with your bare hands. That's where detectors like Super Kamiok come in. Buried a kilometer underground in a Japanese mine, this colossal tank holds 50,000 tons of ultra-pure water. On the rare occasion a neutrino does interact, maybe by striking an atomic nucleus, it creates a faint blue flash called Cherenkov radiation, a cosmic fingerprint picked up by thousands of sensitive phototubes lining the tank. Even with this precision, most neutrinos pass right through unnoticed. The ones we do catch tell stories of stellar processes we'd otherwise never see, like the slow death throes of a red giant or the shockwaves rippling through a supernova's core. And then there are the cosmic oddballs, neutrinos that shouldn't exist. In 2013, the Ice Cube detector in Antarctica spotted two ultra-high-energy neutrinos, nicknamed Bert and Ernie, with energies 1,000,000 times greater than those from our Sun. Their origin, likely a blazar, a supermassive black hole spewing jets of plasma directly at Earth. These extreme neutrinos are like interstellar bullets, punching through the galaxy with enough force to reveal environments where matter is shredded by forces we can't yet replicate. But the real magic lies in what neutrinos might teach us about the universe's hidden architecture. Some theories suggest they could be the key to dark matter, or even clues to why the cosmos is made of matter instead of antimatter. Every time we detect one, whether from the Sun, a dying star, or the depths of space, it's like intercepting a coded message from the universe's most secretive corners. The challenge isn't just finding them, it's learning how to listen. Baryon acoustic oscillations sound like something from an astrophysics textbook, but they're actually one of the universe's most fascinating echoes. Picture the newborn cosmos just 380,000 years after the Big Bang. A seething plasma so dense light couldn't travel more than a fraction of an inch before bouncing off particles. In this primordial soup, gravity pulled matter inward while radiation pressure pushed it outward, creating colossal sound waves that rippled through the universe like a cosmic drumbeat. Then, in an instant, everything changed. As space expanded and cooled, atoms formed, light broke free, and those pressure waves froze in place, leaving an indelible imprint on the cosmos. Today, that imprint lingers as a subtle pattern woven into the distribution of galaxies. Imagine the universe as a vast sheet of graph paper, with galaxies clustered at regular intervals about 500 million light-years apart. This isn't random. It's the fossilized remnant of those ancient sound waves, stretched to cosmic proportions by billions of years of expansion, the wild part. We can still detect this rhythm by mapping millions of galaxies with projects like the Sloan Digital Sky Survey. Astronomers have spotted this statistical fingerprint, a whisper from a time when the universe was 1,000 times smaller and 1,000,000 times hotter. But these oscillations aren't just relics, they're rulers, because we know the original wavelength of those primordial sound waves. They act as a standard measuring tape for the universe. By comparing the expected size of these patterns to how they appear in galaxy surveys, scientists can track how space itself has stretched over time. This is how we confirm the universe's expansion is accelerating. driven by the mysterious force we call dark energy. The oscillations even hint at dark matter's influence, revealing how its invisible gravity sculpted the early cosmos. The most tantalizing possibility: these frozen waves might help us map the cosmic web's hidden threads, the vast, spider-like network of dark matter that underpins everything we see. Simulations suggest baryon acoustic oscillations should align with these filaments, tracing the scaffolding that guides galaxy formation. Future telescopes, like the Dark Energy Spectroscopic Instrument, aim to chart this structure in unprecedented detail, potentially uncovering new physics lurking in the gaps between galaxies. So the next time you look at a galaxy cluster, remember, its position isn't just a point in space. It's part of a rhythm, a vibration left over from the universe's first moments. And that rhythm might hold the key to everything we don't yet understand. The universe teems with possibilities: billions of galaxies, trillions of stars, countless planets. Statistically, we shouldn't be alone, yet the cosmos remains eerily quiet. This is the Fermi Paradox, the glaring contradiction between the high probability of extraterrestrial life and the total lack of evidence for it. Named after physicist Enrico Fermi, who famously asked, "Where is everybody?" the paradox forces us to confront uncomfortable truths. If civilizations are common, why haven't we heard a single whisper across the cosmic ocean? One chilling possibility is that advanced civilizations are hiding not just from us, but from everyone. Imagine a universe where survival means staying silent, where broadcasting your location invites catastrophe. This is the dark forest hypothesis, inspired by the idea that the cosmos might be like a forest at night, where every creature stays quiet to avoid attracting predators. A civilization that announces itself risks annihilation by something far more advanced or far more paranoid. In this scenario, the voids between stars aren't just empty, they're strategic. A species might deliberately nestle in the darkness, using rogue planets or interstellar dust clouds as cover, their signals intentionally faint to avoid detection. Then there's the sheer brutality of space itself. Even if a civilization masters interstellar travel, the distances are unimaginably vast. Proxima Centauri, our nearest stellar neighbor, is 4.2 light-years away. At current technology speeds, reaching it would take tens of thousands of years, and that's just the closest star. The energy required to cross galactic distances might make large-scale expansion impossible, trapping civilizations in isolated pockets. Add to that cosmic hazards, gamma-ray bursts sterilizing entire regions, rogue black holes wandering unseen, or the slow erosion of resources over cosmic timescales, and the challenge becomes existential. The silence might not mean we're alone, but that the universe is simply too unforgiving for anyone to last long enough to be heard. But not all explanations are so grim. Some scientists argue we might be looking for the wrong things. Our searches focus on radio signals, but an advanced civilization might have moved beyond such primitive technology. They could communicate via neutrino beams, quantum entanglement, or structures we can't yet conceive. Or perhaps they've transcended physical form, uploading their consciousness into vast digital networks, leaving the material universe behind entirely. In that case, the stars might be full of life, just not the kind we're equipped to recognize. The paradox deepens when you consider time. The universe is 13.8 billion years old, Earth just 4.5 billion. Intelligent life could have risen and fallen countless times before we even existed. Their artifacts, mega-structures, probes, or signals might still be out there, buried in the noise of the cosmos or eroded by eons of cosmic radiation. We could be like ants stumbling through the ruins of a long-dead civilization, oblivious to the relics beneath our feet. Ultimately, the Fermi Paradox isn't just about aliens. It's a mirror. Every possible answer reflects our own fears, hopes, and limitations. Whether we're alone, hiding, or simply too early to the party, the silence between the stars forces us to confront the fragility of intelligence in a vast and indifferent universe. And that makes the search and the mystery more profound than ever. Deep in the frigid darkness between stars, a silent alchemy is at work. Tiny grains of dust, no larger than smoke particles, drift through the void, their surfaces sheathed in layers of ice so thin they'd vanish in sunlight. But these aren't ordinary frosts, they're cosmic freezers preserving molecules like water, methane, and ammonia at temperatures just a few degrees above absolute zero. In this frozen state, they wait for millennia, for eons, until a chance encounter with the warmth of a newborn star triggers reactions that could rewrite the story of life itself. Consider the chemistry unfolding on these microscopic ice mantles. When ultraviolet light or cosmic rays strike them, bonds break and reform in unexpected ways. A water molecule might lose a hydrogen atom, leaving behind a reactive hydroxyl radical. That radical could then collide with a carbon monoxide molecule, forming formic acid, a compound found in ant venom and, crucially, in the building blocks of proteins. Over time, these simple reactions build complexity. Methanol transforms into formaldehyde, which links up to form sugars like ribose, the backbone of RNA. It's as if the universe has preloaded these ices with a toolkit for biochemistry, waiting for the right conditions to assemble life's puzzle pieces. The evidence is everywhere. Telescopes like ALMA have spotted glycolaldehyde, a sugar molecule in the gas clouds around young stars. The Rosetta mission found amino acids like glycine on Comet 67P, frozen relics from the solar system's infancy. Even meteorites recovered on Earth contain nucleobases, the letters of genetic code. These discoveries suggest that the ingredients for life aren't rare flukes, but inevitable products of cosmic chemistry. But here's the twist. These ices might do more than just store ingredients, they could actively protect them. In the harsh radiation of space, complex molecules would normally be torn apart. Yet layered ice acts as a shield, absorbing destructive energy while allowing slower, more constructive reactions to occur beneath its surface. Some experiments even show that ice's crystalline structure can align molecules in ways that make chemical handshakes more likely, like a microscopic assembly line. The implications are staggering. If this process works near young stars, it could be happening right now in the frozen plumes of Saturn's moon Enceladus, or beneath Europa's icy crust. Or perhaps on rogue planets, drifting far from any sun, where radioactive decay keeps subglacial oceans liquid for billions of years. Life might not need a warm, sunlit pond to begin, just time, the right chemistry, and a blanket of interstellar ice to keep the recipe safe until conditions are right. What we're witnessing is a universe that doesn't just tolerate life, but actively prepares for it. Every molecular cloud, every comet, every icy grain could be a time capsule carrying the seeds of biology across the galaxy. The next time you see frost on a window pane, remember, that delicate crystal lattice might hold the blueprint for existence itself, and it's been writing that story since long before Earth was born. Somewhere in the darkness between stars, relics from the universe's violent birth might still lurk, black holes no larger than a grapefruit, yet weighing as much as a mountain. These aren't the collapsed corpses of dead stars we're familiar with. They're primordial black holes, hypothetical remnants of the Big Bang itself, when the newborn universe was so dense that random fluctuations in density could have collapsed directly into singularities. Picture space-time in those first chaotic seconds, a seething, frothing sea where pockets of matter squeezed tight enough to punch holes in reality. most evaporated instantly, vanishing in bursts of Hawking radiation. But the ones that survived, they could still be out there, drifting unseen through our galaxy like cosmic landmines. What makes these ancient objects so compelling is how they might solve two mysteries at once. If they're abundant enough, they could account for dark matter, the invisible glue holding galaxies together. Unlike exotic particles that have eluded detection for decades, primordial black holes wouldn't require new physics. They'd just be, well, ordinary black holes, albeit ones formed under extraordinary conditions. Some theories suggest they congregate in halos around galaxies, their collective gravity sculpting the cosmos while remaining utterly invisible. Others propose they hide in plain sight within our own solar system, their faint gravitational tugs occasionally perturbing the orbits of distant objects like the hypothetical planet 9. But there's a darker edge to this idea. A wandering primordial black hole passing near Earth would be catastrophic. Though small, its gravity would distort our planet's orbit, trigger earthquakes, and rip apart anything that ventured too close. Even a distant encounter could fling comets from the Oort Cloud toward the inner solar system, raining destruction over millennia. The good news, the odds are astronomically low. Space is vast, and these objects, if they exist, are likely rare. Still, their potential presence adds a thrilling tension to interstellar exploration. Future starships might need to map not just stars and planets, but the invisible pits of gravity hiding in the void. The hunt for these cosmic ghosts is already underway. Scientists scour telescope data for fleeting lensing events, sudden brightenings of distant stars as an unseen object's gravity bends their light. Others study the precise timing of pulsars, watching for minuscule hiccups that might betray a black hole's passage. Even gravitational wave detectors like LIGO could stumble upon them, catching the ripples from a primordial black hole colliding with a neutron star or another black hole. Finding one would rewrite cosmic history. It would prove the early universe was wilder and more chaotic than we imagined, with black holes forming before the first stars even ignited. It might reveal dark matter's true face, not as an exotic particle, but as a swarm of ancient singularities left over from creation. And it would remind us that the universe's deepest secrets aren't always hidden in distant galaxies. Sometimes they're right beside us, woven into the fabric of the dark. The Kuiper belt is like a frozen archive at the edge of our solar system, a vast ring of icy debris stretching from Neptune's orbit out to about 55 astronomical units. Here, dwarf planets like Pluto and Haumea glide through the darkness alongside millions of smaller bodies, remnants of the solar system's formation over 4 billion years ago. These aren't just inert chunks of ice. They're time capsules preserving compounds unchanged since the dawn of our cosmic neighborhood. When one gets nudged by a gravitational kick, perhaps from Neptune or a passing star, it can tumble inward, transforming into a comet with a glowing tail as it nears the sun. But the Kuiper belt is just the beginning. Further out lies the scattered disk, a sparser population of objects with wild, elongated orbits. These icy nomads, like Eris, which briefly dethroned Pluto as the solar system's 9th planet, trace paths that take them hundreds of astronomical units away before swinging back toward the sun. Their chaotic trajectories suggest a turbulent past, possibly shaped by an ancient upheaval in the solar system, like the outward migration of Neptune or the gravitational influence of a long-lost sibling star. Beyond the scattered disk, the space between our solar system and the stars isn't empty. It's a transitional zone where the sun's gravity weakens but hasn't yet vanished the inner Oort Cloud. This vast, diffuse shell of icy bodies stretches from around 2,000 to 20,000 astronomical units, a region so distant that the Sun would appear as just another bright star. Unlike the flat Kuiper belt, the Oort Cloud forms a spherical halo around our solar system, its objects orbiting in all directions like bees around a hive. What makes these distant realms so fascinating is how they blur the boundary between our solar system and interstellar space. Comets from the Oort Cloud, like the dazzling Hale-Bopp, carry material that might have originated near other stars. Some scientists speculate that a fraction of these icy bodies could be interstellar interlopers, captured by the Sun's gravity during its journey through the galaxy. Others wonder if the Oort Cloud might be seeding nearby star systems with its own ejected objects, a cosmic exchange program operating on million-year timescales. Every time we study one of these distant wanderers, we're peering into a hidden chapter of our solar system's history. The chemicals locked in their ice could reveal how water and organic molecules were delivered to Earth. Their orbits hint at long-forgotten gravitational dramas that reshaped the outer solar system, and their very existence challenges our definitions. Where does our cosmic neighborhood end and the great beyond begin? The answer might not be a clear line, but a gradual fading, like a whisper dissolving into the dark. When Comet 2I/Borisov streaked through our solar system in 2019, it wasn't just another icy visitor, it was a stranger. Unlike every other comet we'd seen, this one moved too fast, on a trajectory so extreme it could only have come from another star. For the first time, scientists held a front-row seat to study an interstellar object in detail, and what they found was astonishing. Borisov's composition wasn't alien at all. Its gases, cyanogen, carbon monoxide, water vapor, mirrored those of comets born in our own solar system. This raised a tantalizing possibility. Maybe the ingredients for planets and life aren't unique to us. Maybe the universe cooks with the same recipe everywhere, but Borisov was just the beginning. Years earlier, the bizarre, cigar-shaped Oumuamua had zipped past the Sun, leaving astronomers scrambling to explain its strange acceleration and lack of a visible tail. Some speculated it might be a shard of a shattered planet, ejected by a distant cosmic collision. Others wondered if its odd shape hinted at exotic ices that vaporized unseen, giving it a silent push. The truth we may never know. By the time telescopes caught it, Oumuamua was already racing away, a fleeting messenger carrying secrets we couldn't decipher. These interstellar interlopers challenge our assumptions. If objects like Borisov and Oumuamua are common, and calculations suggest thousands might be passing through the solar system unnoticed at any given moment, then the boundary between star systems is far more porous than we thought. Planets, asteroids, and comets might not stay bound to their birthplaces forever. Gravitational tugs from passing stars or galactic tides could pluck them free, sending them wandering the Milky Way like cosmic driftwood. Some might even carry hitchhikers, microbes frozen in ice, shielded from radiation, surviving eons between the stars. The key to unlocking these mysteries lies in catching the next visitor before it's gone. Projects like the Vera Rubin Observatory, with its massive mirror and ultra-sensitive camera, will scan the skies nightly for faint, fast-moving dots. If we're lucky, we might spot an interstellar comet years before its closest approach, giving us time to launch a probe. Imagine intercepting one, sampling its ices, and holding a piece of another star system in our hands. The data could reveal whether carbon-rich chemistry, the kind that builds life, is universal or a fluke of our cosmic neighborhood. What's most thrilling is the sheer unpredictability of these guests. The next one could be pristine, a frozen relic from a protoplanetary disk we've never seen. Or it might be bizarre, packed with molecules that defy our understanding of chemistry. Either way, each visitor is a postcard from the unknown, reminding us that the universe is far more connected and far stranger than we ever imagined. Gravitational waves are the universe's silent tremors, ripples in the very fabric of space-time itself, sent racing across the cosmos by the most violent events imaginable. Picture two black holes, each billions of years old, locked in a final, deadly dance. As they spiral closer, their immense gravity distorts space like a stone dropped in a pond, sending out waves that stretch and compress everything in their path. By the time these waves reach Earth, they're barely detectable, warping our planet by less than the width of an atom. Yet in 2015, the Laser Interferometer Gravitational Wave Observatory, or LIGO, caught the first clear signal of this phenomenon, a fleeting chirp confirming Einstein's century-old prediction. What's astonishing is how much these whispers reveal. Each wave carries a fingerprint of its origins, the masses of the colliding objects, their spin rates, even the direction they came from. When neutron stars collide, the waves come paired with flashes of gamma rays and showers of heavy elements like gold and platinum, proof that these cataclysms forge the building blocks of planets and life itself. But the real magic lies in what gravitational waves can sense that light cannot. Black holes, by their very nature, emit no light, yet their mergers send tremors through space-time that cross billions of light-years unimpeded, offering a direct window into the invisible. This raises a tantalizing possibility. Could gravitational waves expose hidden objects lurking in the voids between stars? The universe is filled with mass we can't see, rogue black holes drifting alone, dark matter clumps, or even exotic relics from the Big Bang. Traditional telescopes rely on light, but gravitational waves don't care if something is dark or bright. They feel the gravity. Future observatories, like the Laser Interferometer Space Antenna, or LISA, will extend our reach into space, free from Earth seismic noise. With sensitivity tuned to lower frequencies, it could detect the mergers of supermassive black holes, the subtle tug of intermediate mass black holes wandering the galaxy, or even the faint ripples from cosmic strings, hypothetical defects in space-time left over from the universe's birth. The implications are staggering. If unseen masses are warping space-time in ways we've yet to measure, gravitational waves could map them like sonar probing the ocean depths. A hidden population of primordial black holes might explain dark matter's grip on galaxies. Strange, quark-filled stars, more exotic than neutron stars, could leave distinct signatures in the waves' patterns. Even the structure of space-time itself might ripple differently in regions where dark energy's repulsive force is strongest. Every new detection peels back another layer of the cosmic unknown. Gravitational waves don't just let us hear the universe, they let us feel it, tracing the contours of reality in ways light alone never could. And as our detectors grow more sensitive, who knows what voices we'll find in the dark, whispering secrets from the void. The Drake equation has haunted and fascinated astronomers for decades, a simple formula estimating how many intelligent civilizations might share our galaxy. But the vast emptiness between stars, once seen as just empty space, could hold the key to why we haven't found anyone else yet. Take the equation's first term, the rate of star formation. We now know the Milky Way churns out about 7 new stars per year, many with planets. But the next factor, how many of those planets are habitable, has dramatically shifted. Kepler data revealed Earth-sized worlds in the Goldilocks zone are staggeringly common, with billions likely scattered across the galaxy. Yet the real bottleneck might be the voids between these oases. Even if life emerges frequently, the average distance between stars is over 4 light-years, a gulf that could isolate civilizations for millennia. Imagine a thriving society around Proxima Centauri, just 4 light-years away. If they sent radio signals a century ago, we'd only now be hearing their first whispers, and that's our closest neighbor. Expand to the galaxy's 100,000 light-year span, and signals from distant civilizations might drown in cosmic noise before reaching us or arrive long after their senders have vanished. Then there's the dark forest hypothesis, the chilling idea that advanced civilizations stay silent to avoid attracting predators. In this scenario, the emptiness between stars isn't just a barrier, it's a strategic buffer. A species might cloak its presence, masking heat signatures or using neutron stars as natural lighthouses to communicate covertly. The voids become hunting grounds where breaking silence could mean extinction. If true, the Drake equation's final term, the lifespan of detectable civilizations, might be shockingly low, snuffed out by cosmic Darwinism, but modern revisions offer hope. Breakthroughs in astrobiology suggest life could thrive in more places than we thought: subsurface oceans on icy moons, rogue planets warmed by radioactive decay, or even gas giants with floating microbial colonies. Each discovery nudges the equation's variables upward. Meanwhile, new telescopes like the Square Kilometre Array could detect not just intentional signals, but the accidental buzz of alien technology, leaked radar, industrial byproducts, or the infrared glow of megastructures. Perhaps the most profound shift is temporal. The galaxy is 13 billion years old. Civilizations might rise and fall in waves, their epochs separated by gulfs of time as well as space. We could be like ants scurrying across the ruins of a long-dead city, oblivious to the towers that once stood there, or we might be among the first, with others still to come. The silence isn't necessarily absence. It might just mean we're learning to listen in the wrong places, at the wrong times, or with the wrong tools. Every recalibration of the Drake equation doesn't just change a number, it reshapes how we see our place in the cosmos. And that's the real power of the void. It doesn't just separate stars, it keeps the universe's greatest secrets just out of reach, waiting for us to look deeper. Exoplanets orbiting dim red dwarfs or drifting alone in the interstellar void exist in a perpetual state of twilight worlds where the sun never rises and the sky is forever black. These aren't the planets we're used to imagining. On a rogue planet untethered from any star, temperatures could plunge to -270 degrees Celsius, cold enough to freeze atmospheres solid. Yet beneath icy crusts, tidal heating or radioactive decay might maintain vast subsurface oceans, hidden pockets of liquid where life could cling in utter darkness. Even around faint red dwarfs, tidally locked planets might host eternal twilight zones, narrow bands where feeble starlight creates a fragile balance between scorching daysides and frozen nights. Detecting these shadowed worlds requires tricks beyond traditional transit methods. Microlensing, where a planet's gravity briefly magnifies the light of a distant star like a cosmic magnifying glass, has already revealed free-floating planets that outnumber stars in our galaxy. Some could be gas giants ejected from violent young solar systems, others rocky worlds flung into the abyss by gravitational chaos. The most tantalizing are steam planets, theorized to form in the icy outskirts of star systems before migrating inward. These could harbor thick, warm atmospheres rich in water vapor, their surfaces shrouded in permanent fog under dim red suns. The chemistry of these environments defies earthly logic. Around ultra-cool dwarfs, photosynthesis as we know it might be impossible, but some microbes on Earth thrive on infrared radiation, hinting at alien life forms that could harvest energy from wavelengths invisible to us. Hydrothermal vents in subsurface oceans might host ecosystems entirely independent of sunlight, like those in Earth's deepest trenches. or perhaps exotic solvents like liquid methane could replace water, supporting biochemistry we've yet to imagine. Then there's the question of time. Red dwarfs burn for trillions of years, offering stable environments far longer than sun-like stars. A civilization arising on such a world would witness cosmic epochs unfathomable to us, watching as galaxies collide and stars fade around their eternal dim hearth. The silence between these worlds might not be emptiness but patience. Every new microlensing event, every faint infrared signature, peels back another layer of this hidden cosmos. The darkness isn't barren, it's a frontier waiting to rewrite what we think we know about where and how life can exist. On the night of August 15, 1977, a radio telescope in Ohio picked up something extraordinary, a signal so strong it made astronomer Jerry Amon circle it on the printout and scribble, "Wow." In the margin, it lasted 72 seconds, blaring at a frequency near the hydrogen line, a logical choice for interstellar communication. Then, just as suddenly as it appeared, it vanished. 46 years later, we still don't know what caused it. The signal's intensity suggested a source far beyond our solar system, possibly from the constellation Sagittarius. But here's the catch: after thousands of follow-up scans, it never repeated, not once. This wasn't static or a passing satellite. The WOW signal's narrowband frequency ruled out most natural phenomena, pulsars, quasars, or stellar flares. Its structure was eerily artificial, like a deliberate broadcast, yet the void it seemed to come from holds no known stars or planets within that range. One theory suggests it could have been a cosmic coincidence, a signal from a distant civilization, briefly amplified by the gravity of an intervening object, bending the radio waves toward Earth like a lens before the alignment shifted. Another proposes it was a reflection off space debris, bouncing a human transmission back at us from an unexpected angle, but neither explanation fully fits the data. The real enigma is the silence that followed. If it was a deliberate message, why just one pulse? Civilizations capable of interstellar communication would likely repeat their signals, ensuring they'd be heard. Unless, and this is where it gets haunting, the sender did repeat it, and we simply missed the follow-up. The Big Ear telescope that detected WOW couldn't swivel to track the source. By the time other telescopes looked, the moment had passed. Or perhaps the signal wasn't meant for us at all, but for someone or something else, and we just happened to eavesdrop on a cosmic conversation. Then there's the darker possibility that the signal wasn't a hello but a goodbye, a dying civilization's final transmission cut short by catastrophe. Or a beacon malfunctioning as it drifted between stars, its power source fading into the void. The more we learn about the fragility of technological societies, asteroid impacts, gamma-ray bursts, even self-destruction, the more plausible this becomes. The WOW signal might be a fossil, a single ripple from a civilization that flared bright and vanished long before humans walked the Earth. Yet hope isn't lost. Modern projects like Breakthrough Listen scan millions of frequencies simultaneously, with algorithms designed to catch fleeting signals. New telescopes, like the upcoming Square Kilometre Array, will comb the sky with unprecedented sensitivity. If another WOW comes, we'll be ready. But until then, it remains a tantalizing riddle, a whisper from the dark that refuses to be forgotten, reminding us that the universe is vast, strange, and far from silent. We just need to learn how to listen. Crossing the void between stars isn't just a test of engineering, it's a confrontation with the fundamental limits of physics. Take Proxima Centauri, our nearest stellar neighbor at 4.2 light-years away. With today's chemical rockets, the journey would take over 70,000 years. That's longer than all of recorded human history just to reach the closest star. But what if we could cheat the clock? Light sails, gossamer thin sheets propelled by lasers, could theoretically reach 20% the speed of light, cutting the trip to a mere 20 years. Imagine a spacecraft no heavier than a smartphone, its sail thinner than a soap bubble, riding a beam of light like a cosmic surfboard. The Breakthrough Starshot initiative aims to do just that, launching swarms of microprobes to skim past Proxima Centauri's planets, snapping photos as they blaze by at impossible speeds. Then there's the brute force approach, fusion drives. Unlike today's rockets, which burn fuel like a matchstick, fusion would harness the same nuclear fire that powers stars. Picture a ship like Project Daedalus, a colossal vessel fueled by pellets of helium-3 mined from lunar soil or gas giants. Its engines would detonate these pellets in controlled bursts, creating a continuous nuclear firestorm to push the ship forward. At 12% light speed, Barnard's star 6 light-years away could be within a human lifetime's reach. The catch: we've yet to sustain fusion for more than seconds in labs, let alone tame it for propulsion. But the real game-changer would be wormholes, cosmic shortcuts bending space-time itself. Einstein's equations suggest these tunnels could exist, linking distant points like a folded piece of paper pierced by a needle. Traversing one might take minutes instead of millennia. The problem: wormholes demand exotic matter with negative energy to stay open, a substance we've never observed. Even if they exist, they might be microscopic or unstable, collapsing the instant anything enters. Yet the mere possibility ignites the imagination. A network of wormholes could transform the galaxy into a subway map, with humanity hopping between stations like commuters. The psychological hurdles are just as daunting. Generation ships, self-sustaining arcs where entire lineages live and die en route raise eerie questions. Would descendants born in the void still care about a planet their ancestors left centuries ago? Or consider hibernation, slowing metabolism to near zero, letting astronauts sleep through the centuries? We've seen tardigrades survive the vacuum of space. Could we engineer similar suspended animation for humans? Perhaps the most profound limitation isn't technology, but time. Civilizations rise and fall in mere millennia. Even at light speed, the Milky Way's 100,000 light-year span means messages or ships would outlast the cultures that launched them. The universe might be filled with the ruins of ambitious species who reached for the stars but vanished before their ships arrived. Yet history whispers that impossible barriers exist to be broken. 500 years ago, oceans were as unconquerable as interstellar space seems today. The voids between stars may yet become highways if we dare to rethink what's possible. The universe isn't just expanding, it's accelerating, as if some unseen hand is pressing down on the cosmic gas pedal. This baffling discovery, which earned the Nobel Prize in 2011, hinges on a force so mysterious we've only named it by what it isn't: dark energy. Think of it as the anti-gravity of the cosmos, a repulsive pressure woven into the fabric of space itself. Unlike dark matter, which clumps around galaxies like invisible glue, dark energy thrives in the voids, those vast, almost empty regions between galaxy clusters. There where matter is thinnest, its push seems strongest, stretching the universe apart faster with every passing second. What makes dark energy so unsettling is how little we understand it. The leading theory suggests it's the cosmological constant, a term Einstein once called his greatest blunder, representing the energy of empty space itself. Quantum physics tells us a vacuum isn't truly empty. It crackles with virtual particles flickering in and out of existence. If these fluctuations generate energy, they could explain the accelerating expansion. But here's the problem. When physicists calculate how much energy this quantum foam should produce, the number is off by a factor of 10 to the power of 120. That's not just a rounding error, it's the largest discrepancy between theory and observation in all of science. Then there's the phantom in the equations, phantom energy, a hypothetical form of dark energy that grows stronger over time. If this variant exists, the universe's fate could be far more violent than a slow fade into cold darkness. Space itself might eventually tear apart in a big rip, shredding galaxies, stars, and even atoms as expansion outmuscles every fundamental force. Alternatively, dark energy could decay, reversing its effect and collapsing the universe in a big crunch. Or it might simply persist, stretching the cosmos into an ever thinner, ever colder void where galaxies vanish over the horizon of visibility, leaving future astronomers with an empty sky. The stakes couldn't be higher. Dark energy makes up 68% of the universe's total energy budget, more than dark matter and ordinary matter combined. Its behavior holds the answer to whether the cosmos will end in fire, ice, or something stranger. Projects like the Dark Energy Survey and the upcoming Euclid Space Telescope are mapping billions of galaxies to trace expansion's history, hunting for clues in the subtle warping of light around cosmic voids. Even gravitational wave detectors might help, as the ripples from distant collisions could reveal how space has stretched over eons. Yet the most tantalizing possibility is that dark energy isn't a force at all, but a sign we've misunderstood gravity itself. Modified theories like Myst propose that Einstein's equations break down on cosmic scales, eliminating the need for dark energy entirely. Others suggest it's a shadow of extra dimensions, or evidence of a multiverse where our universe is one bubble among countless others, each with its own physics. One thing's certain, dark energy is the ultimate cosmic wildcard. It's the reason the night sky still holds mysteries after millennia of observation, and the proof that the emptiest places in the universe might be the most powerful. Every measurement, every failed theory brings us closer to a truth that could rewrite not just cosmology, but our very understanding of reality. And that's the real magic of the void. It's not empty. It's alive with questions. Cosmic strings might sound like science fiction, but they're one of the most intriguing what-ifs in modern physics. Picture the universe in its earliest moments, a seething, ultra-hot soup of energy. As it expanded and cooled, phase transitions rippled through space-time, like cracks forming in ice as water freezes. Some theories suggest these cracks didn't smooth out. Instead, they froze into place as cosmic strings, infinitesimally thin threads of pure energy, thinner than a proton but denser than a mountain range. Each one would stretch across the cosmos like a guitar string tuned to the fabric of reality itself, vibrating with the echoes of creation, the mind-bending part. Their gravity wouldn't come from mass but from sheer distortion. A cosmic string warps space-time so intensely that if one passed through a room, you could see the back of your own head. Light would bend around it like water swirling down a drain. Galaxies might form along these filaments like beads on a necklace, their peculiar alignments hinting at invisible scaffolding. Some models even suggest strings could create double images of distant quasars, their gravity splitting light like a cosmic prism. Detecting them would require a blend of patience and ingenuity. Unlike black holes, strings leave no shadow. Instead, astronomers hunt for their fingerprints in the cosmic microwave background, the afterglow of the Big Bang. A moving string would create sharp, linear temperature variations in this radiation, like a knife dragged through frosting. Others search for abrupt jumps in the light of distant stars, signs that a string's gravity briefly magnified their brightness as it passed between us and them. The most tantalizing clue might come from gravitational waves. If two strings cross or snap, Simulations show they'd send out ripples in space-time with a unique, high-pitched frequency, a cosmic ping, unlike anything from black hole mergers. What makes cosmic strings so captivating isn't just their strangeness, but what they'd reveal. Finding one would confirm that the early universe underwent phase transitions beyond the standard model, opening doors to theories like grand unification or even string theory. They might explain why some galaxy clusters move inexplicably fast, as if tugged by invisible threads, and if strings carry electric currents, as some models suggest, they could power the most extreme particle accelerators in nature, firing cosmic rays with energies we can't replicate on Earth. Yet the ultimate irony is their fragility. A single cosmic string, if it exists, might weigh more than a galaxy compressed into a line thinner than an atom, but brush it with your hand and you'd feel nothing. It's the universe's most dramatic whisper, a scar from its birth that could rewrite physics if only we learn how to see it. The vast emptiness between stars might not be the final frontier. It could be just the first curtain in a cosmic theater with countless stages. Imagine our universe as a single bubble floating in an infinite ocean of foam, each bubble a separate reality with its own unique laws of physics. This is the multiverse hypothesis, a radical idea gaining traction among cosmologists. Some versions suggest these alternate universes could be mere millimeters away in higher dimensions, yet forever out of reach, separated by membranes of space-time thicker than galaxies. Other theories propose they're scattered across an endless inflationary landscape, born from quantum fluctuations in an eternal cycle of cosmic birth and death. Consider the implications. In one universe, gravity might be 1,000 times stronger, crushing matter into black holes before stars can form. In another, the electromagnetic force could be too weak for atoms to bond, leaving only a diffuse haze of particles. There might even be realms where time runs backward or entropy decreases, creating worlds where effects precede causes, the most haunting possibility. Some of these universes could host civilizations asking the same questions we are, trapped in their own observable bubbles, unaware of the others just beyond the veil. The evidence, while indirect, is tantalizing. The cosmic microwave background, the afterglow of the Big Bang, shows peculiar anomalies like cold spots and asymmetries that some theorists argue could be bruises from collisions with other universes during inflation. Others point to the eerily precise fine-tuning of our universe's constants. Why is gravity exactly strong enough to allow stars but weak enough to let them burn for billions of years? If countless universes exist with random parameters, ours might simply be one where life could arise to notice the coincidence. Yet the multiverse remains controversial. Without a way to observe these alternate realities directly, some critics dismiss it as metaphysics disguised as science, but cutting-edge experiments might change that. Gravitational wave detectors could someday catch echoes of primordial bubble collisions. Quantum computers might simulate alternate physics, and if higher dimensions exist, particle colliders could uncover particles that briefly leak into our universe from neighboring brains. The most profound question isn't whether the multiverse exists, it's what its existence would mean for our place in the cosmos. If infinite versions of reality play out across the void, does that make our lives trivial or miraculous? The answer might lie in the spaces we've yet to explore, not just between stars but between worlds. Astrobiology's greatest twist might be hiding in the most hostile place imaginable, the frozen, radiation-blasted void between stars. Earth's extremophiles have already rewritten the rules for where life can thrive. Tube worms clustered around scalding hydrothermal vents, bacteria buried kilometers deep in Antarctic ice, even resilient tardigrades surviving the vacuum of space. These organisms prove life clings to existence in conditions once thought sterile. Now imagine their microscopic cousins, tucked inside the icy shield of a drifting comet or clinging to a speck of interstellar dust, riding cosmic currents for millions of years. The galaxy could be teeming with such hitchhikers, invisible threads of biology woven through the darkness. Consider the journey of a single microbe frozen into a comet's core. Shielded from radiation by layers of ice, it might survive eons in suspended animation until a chance encounter with a young star's warmth revives it. We've seen hints this isn't just speculation. The amino acids and sugars found on meteorites like Murchison suggest the building blocks of life are not just hardy but cosmically abundant. Some experiments even show bacteria like Deinococcus radiodurans, dubbed Conan the Bacterium, surviving years of simulated space exposure by repairing their own DNA. If life can endure such extremes, why not the vast tracks between stars? The math gets even wilder when you factor in rogue planets. These nomads, untethered from any sun, might outnumber stars in the Milky Way. While their surfaces freeze solid, tidal forces or radioactive decay could keep subsurface oceans liquid. Picture a world like Jupiter's moon Europa, but drifting alone, a dark arc carrying microbial ecosystems through the void. If just one in a million rogue planets hosts life, the galaxy could still harbor billions of such hidden oases. Yet the real game changer would be panspermia, the idea that life spreads between star systems like dandelion seeds. A microbe-laden rock ejected by an asteroid impact on one planet might drift for millennia before landing in another system's ocean. Simulations suggest debris from Earth could have reached nearby stars within a few million years, a blink in cosmic time. If life arose independently on multiple worlds, this process could have smeared it across the galaxy like jam on toast, blending biologies until the universe hums with shared genetic echoes. The challenge is proving it. Future missions like Europa Clipper or probes to Enceladus's plumes might find life with chemistry subtly off from Earth's, a sign of independent origins. Or we could catch a smoking gun, a microbe on a comet with DNA unlike anything terrestrial. Either discovery would shatter the notion that life is bound to planets, revealing the cosmos as a living network where even the void breathes. Until then, the silence between stars feels different, not empty but patient. Every meteorite, every icy grain could be a message in a bottle one we're only beginning to read. The darkness between stars isn't just vast, it's deceptive. For every celestial object our telescopes catch, countless others slip through unseen, hidden by distance, dimness, or the simple fact that they don't play by the rules of light. Take black holes, for instance. Unless they're actively devouring matter and glowing with friction, they're nearly invisible against the void. Even stars can vanish from view. Brown dwarfs, failed stars too cool to ignite nuclear fusion, glow faintly in infrared but often evade optical telescopes entirely. And then there's the real specter of the cosmos, rogue planets, drifting without a sun to illuminate them. These frozen nomads might outnumber stars in the Milky Way, yet they're so faint we've only spotted a handful through sheer luck when their gravity briefly warped the light of a background star. But the limits of observation run deeper than missing objects. The universe is filled with phenomena that don't just hide, they defy detection by design. Dark matter, making up 27% of the cosmos, doesn't absorb, emit, or reflect light. It's a ghost that only betrays its presence by the way it tugs on galaxies, bending their rotation curves into impossible shapes. Then there's the interstellar medium itself, diffuse clouds of gas and dust so thin they're practically transparent. Yet collectively they obscure entire regions of the galaxy, like a cosmic veil drawn over the Milky Way's heart. The irony, some of the universe's most important processes happen in these blind spots. take star formation. The earliest stages occur deep within dense molecular clouds where visible light can't penetrate. Without radio and infrared telescopes, we'd never witness the birth of protostars, their faint heat signatures the only hint of the stellar nurseries taking shape inside. Even neutrinos, those near-massless particles flooding the cosmos, sail through Earth undetected unless they happen to collide with an atom in a tank of ultra-pure water buried deep underground. This is where the next generation of astronomy comes in. Imagine neutrino telescopes, not hunting for light but for the faint flashes these ghostly particles create when they rarely interact. They could map the sun's core in real time or spot supernova hours before the light reaches us. Quantum sensors, leveraging the bizarre precision of entangled particles, might measure gravitational waves with such sensitivity they'd reveal hidden objects, primordial black holes, cosmic strings, or even the vibrations of spacetime itself. And then there's dark matter detectors, buried in old mines to shield them from cosmic noise, waiting for that one in a trillion collision that could finally unmask the universe's dominant yet invisible ingredient. The most tantalizing possibility, these technologies might uncover entirely new classes of objects. Theoretical physicists speculate about quark stars, dense remnants even stranger than neutron stars, or magnetic monopoles, lone north or south poles that could rewrite electromagnetism. There could be entire populations of objects lurking just beyond our current thresholds, waiting for the right tool to reveal them. The void isn't empty. It's a frontier, and every leap in technology peels back another layer of its secrets. What we can't see today might redefine reality tomorrow. The next decade of space exploration promises to peel back the veil on the cosmic unknown like never before. At the forefront is the James Webb Space Telescope, already rewriting the rules of what we thought possible. Unlike Hubble's visible light gaze, Webb's infrared eyes pierce through dust clouds to spy on stellar nurseries hidden in the voids, places where future stars are knitting themselves together from the faintest wisps of interstellar gas. Its recent detection of 6 massive galaxies existing impossibly early in cosmic history, barely 500 million years after the Big Bang, hints that entire chapters of galaxy formation remain missing from our textbooks. These cosmic giants shouldn't have had time to assemble, suggesting either our understanding of dark matter's role is flawed, or the voids between galaxies are far more productive than we imagined. Meanwhile, on Earth's surface, a new generation of radio telescopes is turning the interstellar medium into a cosmic fingerprint. The square-kilometer array, spread across South Africa and Australia, will map hydrogen gas with such precision it could reveal the cosmic webs, hidden threads, the filaments of dark matter along which galaxies arrange themselves like dew on a spiderweb. Its sensitivity might even catch the faint afterglow of the universe's first stars, whose ultraviolet light split primordial hydrogen atoms in an epoch called reionization. Imagine hearing static from a radio built 13 billion years ago. That's the signal astronomers hope to isolate from the noise of the modern cosmos. But the real game changers might be the missions we haven't launched yet. The Interstellar Probe concept, a NASA study for a spacecraft reaching 2,000 astronomical units from the Sun, would venture beyond the heliosphere into true interstellar space. Unlike Voyager's accidental journey, this probe would carry instruments designed specifically to sample the local interstellar medium's chemistry and magnetic fields. It could finally measure the pressure and temperature of the void itself, revealing whether our solar system moves through a typical patch of galaxy or something stranger, like the rarefied aftermath of an ancient supernova bubble. Then there's the tantalizing possibility of catching an interstellar object before it leaves. After Oumuamua and Borisov race through our solar system, astronomers realized we need telescopes like the Vera Rubin Observatory's LSST scanning the entire visible sky every few nights to spot the next visitor early enough to launch an intercept mission. Imagine a spacecraft rendezvousing with a pristine comet from another star system, analyzing ices that have never felt the warmth of any sun. The chemical signatures locked in those frozen gases could tell us whether the recipe for planetary formation differs across the galaxy, or if the building blocks of life are truly universal. What makes this era unique isn't just better technology, but a fundamental shift in perspective. We're no longer content to passively observe, we're learning how to interrogate the void. When the Event Horizon Telescope added new antennas and captured the first image of Sagittarius, a star's black hole, it didn't just show an eerie ring of light. It proved we could turn Earth itself into a planet-sized magnifying glass, resolving details smaller than Mercury's orbit from 26,000 light-years away. Future expansions might image the black hole at our galaxy's core in real time, watching as it gulps down gas clouds and belches out flares of radiation. The ultimate goal, to understand whether the apparent emptiness between stars is truly barren, or if we've been missing something fundamental. Could dark matter particles interact in ways that leave subtle energy signatures? Might quantum fluctuations in the vacuum spawn temporary particles that influence galactic evolution? Every instrument we build is a new sense organ for the species, extending our perception into realms once reserved for theory alone. Within our lifetime, the voids may transform from blank spaces on the map to the most revealing parts of the cosmic canvas, showing us not just where we are, but what we're made of and how rare or common our place in the universe might be. The space between stars isn't just empty blackness, it's a living, breathing frontier crackling with unanswered questions and cosmic riddles. Think of it like standing on the shore of an ocean at night. The surface seems still, but beneath those dark waves, currents twist and unseen creatures dart through the depths. That's the interstellar medium, a place where particles thinner than a whisper shape the fate of galaxies, where rogue planets drift like lost ships, and where dark matter, the universe's silent architect, pulls strings we're only beginning to sense. Every time we point a telescope or launch a probe, we're not just filling gaps in a map. We're cracking open a cosmic history book written in gravity, light, and particles we can't even see yet. Take dark matter. For decades, it's been the ghost in the machine, a placeholder for the 95% of the universe's mass that refuses to interact with light. But what if it's not just one thing? Some theories suggest it could be a zoo of exotic particles, actions, WIMP, or even primordial black holes from the Big Bang. Others propose we've got gravity all wrong, and the voids between galaxies hold clues to rewriting physics itself. The bullet cluster, where dark matter visibly parted ways with normal matter during a collision, was our first real glimpse of this shadowy realm. Yet for every clue, a dozen new questions emerge. Why does dark matter clump around galaxies in halos instead of spreading evenly? Could it interact with itself in ways we haven't detected? The answers might lie in the next generation of detectors, buried deep underground or floating in space, waiting for that one in a trillion collision that could change everything. Then there are the wanderers, rogue planets untethered from any star, adrift in the eternal night. These aren't just curiosities, they're time capsules from the chaos of early solar systems. Some might be icy wastelands, but others could harbor subsurface oceans kept liquid by tidal forces or radioactive decay. Imagine a world where life thrives not under sunlight, but in the glow of hydrothermal vents, its chemistry entirely alien to ours. The more we find, the clearer it becomes. Habitable zones might be far broader than we ever dreamed. And with missions like the Roman Space Telescope set to hunt for these nomadic worlds via microlensing, we could soon have a census of the galaxy's hidden population. What's thrilling is how much we've yet to invent just to keep up with the cosmos's secrets. Quantum sensors could one day map the gravitational ripples from objects too dark for telescopes. Light sails propelled by lasers might chase down interstellar visitors like Oumuamua, snapping close-ups before they vanish, and neutrino observatories, listening to the faintest whispers from stellar cores, could turn the entire universe into a transparent window. Every technological leap doesn't just give us answers, it rewrites the questions. The darkness between stars isn't a void, it's a mirror. The more we explore it, the more we see our own limitations and our boundless curiosity reflected back. Whether it's decoding the hum of gravitational waves or chasing the phantom tug of dark energy, each discovery peels back another layer of the cosmic onion. And here's the beautiful part, we're just getting started. The next great revelation might be hiding in the next dataset, the next flicker of a distant star, or the next strange signal from the deep. So keep looking up. The universe has a way of surprising those who dare to stare into